Alright guys, we're back with 10.3, which is talking about properties of chords. We're going to start off with a theorem. We're going to do, I'm not going to write out the whole proof, but I'm going to walk you through what the proof should look like for this, okay? So this is a theorem that takes place either in the same circle or in congruent circles. Okay, so either in the same circle or in congruent circles, this is the theorem. Two minor arcs are congruent if and only if their corresponding chords are congruent. Okay, so you can see here in this diagram that in this case the chords A, B, and C, D are congruent to each other. That means that those corresponding minor arcs of arc A, B, and arc C, D are going to be congruent to each other as well. Okay, the proof for that, because it's an if or only if, that means it's a biconditional, right? So the biconditional is true in both directions. So for a proof, you'd have to prove it in both directions. So I think rather than writing out one of the proofs, maybe I'll walk you through kind of both ways. Okay, once you do one, the other one becomes more obvious. So let's say, let's talk about this way. So if you're given that the chords are congruent, okay, so if you're given the arcs are congruent, show that the corresponding chords are congruent. So if we had, let's kind of copy this picture up here. So here's we'll do B, here we'll do A, here we'll do C, here we'll do D. Okay, so if the chords, so if the arcs are congruent, okay, so that means they have the same measure. And remember, the measure of a minor arc is equal to the measure of the central angle. So if you drew in, that means that this central angle here, okay, is congruent to this central angle here, okay? And remember, the way I drew it, these almost look like those should be straight and that these are just vertical angles, but they really don't have to be. In fact, I should have drawn it more exaggerated so that it doesn't even look like that. But so you have these congruent arcs, therefore those central angles are congruent. The other thing is that because this is a circle, this is the central angle, that means that each of these segments here are all radii of the circle, okay? And then if you were to connect these, because I'm interested in chord AB, which is not shown, and I'm interested in chord CD, which is not shown, okay, you could see once you draw that stuff in that these triangles are congruent. So triangle, guess I'll make up a circle center here, we'll call this like F. AFB is congruent to triangle DFC, so this is by side angle side, and so that means that AB is congruent to CD by CBCTC. Okay, so that's kind of a walkthrough of how that proof would look if you did it in the other direction. Okay. Wow, what a great circle! Wow, that's a good circle. If you did it in the other direction, so if you were given the congruent chords and trying to prove that the arcs were congruent, you can do that largely the same way. So when you have this here, say the circle F, right? So it's basically the same idea, okay? Except what then you are doing is you're going the opposite direction. So in this case, your triangles are congruent by side, side, side. Okay, again, you have the radii, which means that these angles, okay, are congruent by CBCDC, and then because these angles are congruent, because the central angles are congruent, the corresponding chords are congruent. Or excuse me, the corresponding arcs are congruent. Okay, so that's how you can prove both ways. It ends up being not too bad to use. Okay, so if we have here circle D, we can see here that AB has a length of 9, BC has a length of 9, so the chords are congruent. Okay, so because the chords are congruent, the corresponding minor arcs are going to be congruent as well. So that means if AB is 110 degrees, then arc BC is going to be the exact same, 110 degrees. And if AC is this other arc, this third arc, is 150, okay, then AB is the same thing as BC, so that means that 150 plus the measure of arc AB twice, because BC is the same measurement, that should add up to a full circle. So this gives you 2 times the measure of arc AB is equal to 210 degrees. So it means the measure of arc AB is 105 degrees. Okay, so not bad there. Next property we have, just here quickly discussing the idea of bisecting arcs. Okay, so here we have arc XZ, all right? And just like segments can be bisected, so can arcs. So in this case, the segment, the radius, CY, bisects this arc, okay? And so we just need that definition of bisector for these next 2 theorems, all right? So rather than having you copy them down, I just copied these directly out of the book because they're a little wordy, so we'll just kind of talk about them. This is one of those cases where it's not an if and only if statement, because proving it one way is not exactly the same as the reverse. But these are essentially 2 sides of the same coin, all right? So the first one here is that if you have 2 chords, okay, where that one chord cuts the other one in half and is perpendicular. So one chord is the perpendicular bisector of the other. The one that is doing the bisecting, okay, is a diameter, okay? So that means here QS would be the diameter, because that is the chord that is the perpendicular bisector of another chord, all right? This theorem is pretty much the same thing in reverse. So here, if you know that a chord is a perpendicular bisector, you know it is a diameter. This one, you need a couple of pieces. One is if you know it is a diameter, all right, that is perpendicular, then it will bisect the chord, okay? This isn't too bad to prove, right? So again, this is another one of those cases where it's really much more about triangles than you think, okay? So if you had here a diameter that is perpendicular to this chord, you can see here that now these again are radii, right? We're not there. We are never getting away from triangles, okay? So if you have a diameter like this, and it is perpendicular to a chord, if you draw in the 2 radii, all right, you'll see you have an isosceles triangle, but you don't want to look at the isosceles triangle, right? So this thing is congruent to itself. You want to look at these 2 triangles up here and down here. And so these 2 triangles would be congruent by hypotenuse leg. And then because they're congruent by hypotenuse leg, these pieces are congruent by CBCDC, okay, which means that it is bisected. This whole length is bisected here, all right? Now, this is one of my favorite questions, okay, but it's not really a good one that could end up showing up on a test or anything like that. But I mean, since we're not really doing tests this year, I guess that doesn't matter. But it's such a neat question. And it's the idea of, if you had these 3 bushes, where would you place a sprinkler so that it basically hits all the bushes kind of evenly? So you're looking for a single spot, right? These bushes are not equidistant from each other. Where can I place a sprinkler so that it is equidistant from all of the bushes? So the way to think about this question, because you essentially need the sprinkler to do like this, right? So you need the sprinkler to be kind of curved through here, which means that you really want, because a sprinkler just sprays in a circle, what you really want is these 3 points to be on a circle, which means this question boils down to where is the center of the circle that has these 3 points on the circle, okay? And so the way we find the center of a circle, without really having a bunch of information, is if you can draw a couple of diameters, okay, the diameters will put you at the center of the circle, okay, because all the diameters contain the center of the circle, all right? So what we can do is we can use this previous theorem up here. So if I were to kind of, say, connect these, okay, so this is, don't mind that, this is my $120 calculator falling on the ground, that's fine. So if I were to kind of connect those, that is a little over 2.5 centimeters. Okay, so half of 2.5 is 1.25. So if we did something like this, okay, that were to find the midpoint of those bushes, okay, and say we do the same thing over here. All right, so these are about a little over 4.5 centimeters away from each other. Okay, so that's about 2.25-ish. All right, and if you were to draw in a perpendicular line, like so. All right, so what we're doing here is if I'm creating a perpendicular bisector through these bushes, what I'm doing is I'm essentially using this theorem, okay? So if I have this line, I'm going to say this is a chord of a circle. So if this chord of this circle is acting as a perpendicular bisector of this chord, that means that this line is a diameter, okay? And I'm going to do the same thing here. So if this chord that I'm drawing up and down this way is a perpendicular bisector of this top chord, all right, then it is also a diameter. So we have a diameter going this way, a diameter going this way, which means this should be the center of the circle that contains these 3 points, which means that is exactly where we want the sprinkler to be. All right. So if this were to work out well, all right, so that is just a little above 4.5 centimeters. All right, from here to here, a little over 4.5 centimeters, and here to here, hopefully a little over 4.5 centimeters. Okay, and so that is a construction of where we'd have to put the sprinkler. So if you imagine this is right, so that those are all radii of a circle that is doing something like this. Okay, kind of going around, right? So I just think it's a neat question. It's not an easy one to just ask you and have you just sit here and construct, but I think it's a good one to look at. All right. The more algebraic ones are certainly the easier ones to give you. Okay. So here we have circle J. So that's important to know this is circle J. Remember, circles are named by their centers. So FJ here is a chord, or well, FJ is not the chord, but this segment that contains F and J is a chord that goes through the center. That means this is a diameter. The diameter is perpendicular to chord EG. Therefore, it also bisects the chord EG. That means that 3x plus 16 is equal to 12x plus 7. So if we solve that, subtracting 3 from both sides, 3x, subtracting 7 from both sides, you get x equals 1. That's not the answer to the question. We want EG. EG is the sum of these two smaller chords. So you have x is 1, so this is 3 plus 16, this is 19, plus this element should also be 19. So EG is 38. All right, good. All right. So on to the last piece here. All right. So 3 quick practice questions. So just pause if you can, and then we'll jump right back in here. These are not like zeros. These are degree symbols. This is just 9x and 80 minus x. Okay. So just pause right here. Try these real quick. All right. So here we have, again, BD is a diameter. The diameter is perpendicular. Okay. So that means that these pieces here are congruent. Okay. And so since this part's getting bisected, all right, these pieces are congruent, right? And then the corresponding arcs here are also going to be congruent. Okay, so this is going to be bisecting this arc, right? So those corresponding pieces should be equal to each other. So that means that 9x should be equal to 80 minus x. We can add x to both sides, and then divide by 10. You should get x equals 8, which means CD is 9 times 8 degrees. That's 72 degrees. DE should be congruent to that, so this is also 72 degrees. And then CE is the whole thing. That's 72 plus 72. That's 144 degrees. All right. All right. So the last theorem, all right, is that in the same circle and congruent circles, 2 chords will be congruent if they are equidistant from the center. So if they are equidistant from the center, the chords will be congruent. This is another one that's pretty easy to prove, and if you haven't figured it out by now, guess what? It's actually about triangles. Okay, so if I draw 2 things that are about equidistant from the center, okay, do that, let's say. So that means that this chord should be congruent to this chord, right? So if they're distant, equidistant, right? So the main thing that's going to trip you up here is forgetting that distance must be measured perpendicular. So it means that it implied by saying distant, you have these right angles, okay? And it should come as no surprise that, for the 100th time, I'm just going to draw in the radii, right? So what you have then, because of this, is don't look at the isosceles triangles again. Look at the right triangles. So the right triangles here are congruent by hypotenuse leg, because everyone has the hypotenuse that is the radii of the circle, and then they all have a leg that is this equidistant part from the center. Okay, so that means that all of the corresponding pieces here are congruent. All right, so they are being bisected and they are congruent to each other as a whole. So, what does it look like in a little practice question here? Let's see. These are both 16. Okay, so we have this. Remember, this is an if and only if statement, right? So then these are. This works in both ways. So because QR and ST are congruent to each other, I know that they are equidistant from the center. That means that 2x is going to be equal to 5x minus 9. So if you subtract 2x from both sides, add 9 to both sides, you can find out that x equals 3. So then CU, right? CU is just 2 times 3, which is 6. Do we have any units here? No. Right? And if you plug that in here, these should be the same thing as well. So it would be 15 minus 9, which is 6. All right. Now the practice questions down here. So same idea. ST is 32. CU is equal to CV, which is 12. So if CU and E is equal to CV, they are equidistant. All right. So if these are equidistant, then ST and QR are congruent to each other. All right. That means that QR is going to be the same thing as ST. This is going to be 32. And then just QU, okay, this is getting bisected. So that's the previous theorem before, and you saw when I was trying to prove this that you can see that these are bisected as well, okay? But again, this is the theorem from the previous page where you have essentially this is part of the diameter, right? So if you were to extend CU, okay, or extend CV, you could extend it into a diameter, and if the diameter is perpendicular, then it bisects the chord, okay? So QU is going to be half of that, it's going to be 16. And then the radius of the circle is not given to us here at all, okay? But what you can do, right, if I only draw some of it, right, so we know that this piece here is CV, let's say. So CV is 12, okay? That means this is ST, okay? ST is 32, but we know that that's cut up into 16 and 16. All right. So the radius of the circle, you guys want to draw that in a convenient way, and a lot of times that convenient way is just going to be making yourself a right triangle. So this is 12, 16. So 12, by the way, right, is 3 times 4. 16 is 4 times 4. All right. So this is a 3 times 4, 4 times 4. This will be 5 times 4. This is a 3, 4, 5 right triangle that has been scaled by a factor of 4. So the radius of circle C here should be 20. All right. All right. So not bad, but we are picking up steam. Good luck. Take care. Email me with questions.